Okay, you're on.
Good afternoon, good morning, wherever you are on this planet, and welcome to our SETI Live. So today we are streaming on Facebook, YouTube, Twitch, and we are going to talk about exoplanets. Specifically, we're going to talk about a very interesting mission that's been launched recently called CHEOPS. So to talk about CHEOPS, I invited two remarkable scientists from Europe. They are joining us from Europe right now. So first we have Kate Isaak. Hi, Kate. How are you?
Hello. Thanks for the invitation, Frank.
So Kate is a project scientist for CHEOPS. She's an astrophysicist working at the European Space Agency. It's called ESA as well in Netherlands. Where are you located, Kate, right now?
I'm also in the Netherlands. I'm in a small town near Estec called Leiden. Old university town, very pretty place.
Good, welcome. And joining us as well from another part of Europe, Laetitia Delrez. Hello, Laetitia, how are you?
Hey, I'm very good, thanks. Thanks for having us today.
So Laetitia is an exoplanetary scientist. I took that from your Twitter account. She has a great Twitter account, so follow her on Twitter if you want to. She's a postdoc at the University of Liege and currently a visiting researcher at Geneva Observatory. She's working on the CHEOPS and projects and other projects related to exoplanets. So before entering into the conversation, I just remind you that you can ask questions on our chat on Facebook and also on YouTube. And of course, don't forget to tell us where you're located, where you are following us from, okay? Where are you on this planet? Hopefully you are on this planet. If you are somewhere else, you can also tell us that you are from somewhere else. We are the SETI Institute after all. So Kate, I heard about this mission for quite a while because in fact the PI came to SETI Institute something like 10 years ago to visit the SETI Institute, and he mentioned this mission to us. But tell us, what is CHEOPS?
Well, as you said, Frank, CHEOPS is a science mission to study exoplanets, which launched at the end of last year from French Guiana. CHEOPS stands for Characterizing ExoPlanet Satellite. It's a small satellite, small and perfectly formed, but small also means relatively small in cost, relatively small in size, but also relatively small in the time it's taken from the start of the mission to the end. It's a science mission in ESA's science program, and it's a cooperation with Switzerland. The gentleman that you mentioned, so that would have been Willy Benz from the University of Bern. He's the PI of the mission, and he leads the CHEOPS mission consortium.
So CHEOPS is a space satellite. And what is made of, or how do you design a space satellite? What do you have inside this space satellite, and where is it located at the moment?
Well, CHEOPS is in an orbit about 700 kilometers above the Earth, so in an orbit which is somewhat higher than the HST and the ISS, but not so far away in the scheme of science satellites. It has one instrument, one single instrument in its payload, and this is a very high precision photometer. The science of CHEOPS is based around ultra high precision transit photometry, which Laetitia will explain in a little bit more detail. But for this, we've optimized the whole of the satellite and its operations to get very stable, very precise light curves, so we can measure the sizes very precisely of small exoplanets that are already known, that are typically orbiting bright stars.
So is the size of CHEOPS, is it the size of a washing machine, the size of a house?
Yes, good. Yes, indeed. It's maybe an American-sized washing machine. Okay. Indeed, and it's about 300. It's about 300 kilos, so quite small compared to some of the other satellites that you may have heard of, so Herschel or Rosetta or Bepi Colombo. These are all missions which are flown recently in ESA's science program. So small and perfectly formed, but already doing some very interesting science.
Okay, and that was launched from the French Guiana using a Soyuz rocket, right? That's one of the.
Indeed. So Indeed. So it was launched from French Guiana, which is Europe's spaceport. Because it was a small mission, it was on a so-called shared launch. So we were the secondary passenger, piggybacking with another larger mission plus some CubeSats. So it was quite a crowded launch, but very exciting nonetheless. Back in December, and since December we've been working very hard. From the beginning of January, we started the commissioning of the satellite. So checking out the performance of the satellite itself, but also the instrument and what we can actually achieve with the instrument. Does it meet our requirements? How good is the photometry that we'll achieve? And then in mid-March, beginning of April, we moved towards more standard routine operations, having finished in-orbit commissioning. And since the middle of April, we've been doing routine science operations, both observing targets which have been selected by the science team. They have a program which fills 80% of the science time on CHEOPS, but also then starting to observe targets from the so-called guest observers program, which takes 20% of the observing time, and that's open to all. So it's a competitive process which people can apply for, and hopefully people will think to apply.
So that's a perfect transition to ask Laetitia what's her role in this project. And if she can tell us a little bit more about the science, specifically with the CHEOPS telescope.
Yes, so I'm a member of the CHEOPS core science team that Kate just mentioned. So the science team is made up of people from the 10 different European countries, which are contributing to the mission. And to tell you a bit more about CHEOPS science, let me just share some slides. So can you see it?
Mm-hmm.
So this is an artist's picture, showing CHEOPS here. And as Kate mentioned, the science goal of CHEOPS is to observe transiting exoplanets. So what is a transit actually? So when a planet is orbiting around its star and its orbital plane is aligned with our line of sight so that we can see it passing in front of the star, then if we monitor the flux of the star, then we can see a small drop in the flux when the planet is in front of the star and is hiding some parts of the stellar flux. So this is what we call a transit. So by measuring the flux from a star during a transit, we can measure these tiny drops, and from these light curves, so what we call light curve, we can actually constrain the planet properties. Most importantly, the planet size relative to the size of the star, so which is a very important parameter.
Yeah, I remind to our viewers that this technique is being used by other space telescopes. CoRoT is one of the first ones, a European one. Mm-hmm. We have Kepler that we have mentioned because SETI has been involved in the Kepler spacecraft for quite a while, but also TESS, another NASA mission. So this is the same technique, basically, where you don't see the planet itself, but you see the shadow of the planet while the planet is passing in front of its star.
Yes.
Very good. So you get information about this, which are related to the size, but CHEOPS is more than just finding the size of planet. What CHEOPS is all about?
So our main goal with CHEOPS is to observe transits of small planets, so planets with size between that of the Earth and Neptune. And we want to observe these transits with a very high photometric precision to get a very precise measurement of their size. And then when we combine this very precise measurement of their size with some independent information about their mass that we can get using some ground-based telescopes, then we derive the planet's bulk density. And this bulk density is a very important piece of information because it gives us some clues about the type of planets we are dealing with. So is it a planet that is mostly rocky, or is it a bit more gassy? Does it contain water, that kind of stuff. So this is the first very important piece of information to characterize exoplanets. Yeah.
That's great. So from this combining space observation with CHEOPS, you get very good estimate of the size, as you say.
Yeah.
And the radial velocity is a technique that is being used from ground-based telescope to measure the mass. So
Yes.
our viewers often ask, when we see a planet with adaptive optics, we only see the light of the planet. We don't have much information about the planet. We need to use models to do this and to understand what planet we are seeing. In your case, by combining those two techniques to observe a planet, you can get a density, which is very strong, a strong indication of the type of planet we are observing. So
Yes.
density of Earth is typically what, 5.5 grams cc?
Yes, 5.5, yeah.
Density of Saturn and Jupiter is typically 1
point something, yeah.
0.9 for Saturn, 1.1, 1.2 for Jupiter, or something like this. So that's basically a great way for you to know if you're observing some gaseous planet or some terrestrial planets.
Yes.
And that's and there is the between. There is a 3.5 grams cc, which could be icy and rock, like the satellite to Jupiter.
Yes.
So before we go through the science and the first result, I would like to mention that we have a lot of people joining us today from everywhere on this planet, from the UK, from Chile, from California, from Moldova, Scotland, Quebec, Sydney, Australia, Turkey, Oklahoma City, Romania, Rio de Janeiro, Hoover, Alabama, Norway, the Ciudad Victoria de Mexico, Austria, Calgary, Canada, Newcastle in UK, Southeast rural Georgia in the US, Palm Desert in California, Spain, Israel, Surrey in UK. Where are you from, Kate? Exactly. Where did you grow up?
Me, I grew up in Birmingham, which is slap bang in the middle of the UK, about as far as the sea as you can get in the UK. The contrast from where I'm in England.
Tell us. So we have Wisconsin, Catalonia, which is part of Spain, Missouri, Parma, New Jersey, Slovakia, Seattle, Brazil, Kurdistan, Warsaw in Poland, and Los Angeles, not too far away from me in California. So welcome. Today we are talking about the CHEOPS mission with two fantastic astronomers. I interrupted you, Laetitia, when you were just about to show us something interesting. Kind of the first scientific result of CHEOPS, right?
Yep, so this is the first exoplanet light curve of CHEOPS. So in this case, we observed what we call a hot Jupiter, so a gaseous giant planet, which is orbiting very, very close to its star. So the orbital period of the planet is only a few days, like 4.7 days. So 1 year on this planet is 4.7 days long, so that's very short. So very hot. The star is about 3 times larger than our sun. So this is what we call a subgiant. And so we observed a transit of this hot Jupiter in front of this star, and this is the first nice transit light curve that we got with CHEOPS. So you can see here this drop in the brightness of the star, which happened when the planet passed in front of the star. And from this very precise transit light curve, we were able to measure the diameter of the planet very precisely, with a precision of about 4,000 kilometers, which is really remarkable, and about 5 times more precise than the previous measurements made from the ground. So this is kind of a foretaste of the capabilities of CHEOPS.
Yeah, so this light curve, and maybe Kate can tell us a little bit about how you go from a telescope in space to a light curve like this. I'm pretty sure there is a lot of things happening here. It's not just like the telescope is not basically giving you, sending you the equivalent of a fax or an email with the light curve, right? Stuff is happening here. So how do you the scientific?
Yes, as you say, Frank, it's quite an involved process. We not only need to tell us telescope where to point and what to actually do, but we also need to collect the data from the instrument and from the satellite. So there are two places which are very important to CHEOPS and its operations. One is the Mission Operations Center, which is in Spain. And then there's the Science Operations Center, which is run from an office just very close to Laetitia, so from the Geneva Observatory. So the Geneva scientists will make a plan for what will be observed with CHEOPS, and this will be then sent by the Mission Operations Center via a ground station to CHEOPS. And then CHEOPS will in turn observe various targets which have been chosen. So the instrument will point at the targets, collect the data, and then this data will be downlinked via the same ground stations, sent to the Science Operations Center in Geneva, where it's then processed. And there's a data reduction pipeline which takes the data, which is pre-processed, and it corrects the data for instrumental effects and produces a series of images and light curves, which are then sent to the scientists, who can then start to analyze this data. And an example of a light curve is one that's in this plot that Laetitia showed. A little bit processed with some additional analysis and detrending, so-called detrending, taking out additional effects that we see due to the telescope. But in principle, it's the light curve that comes from CHEOPS that is being shown.
Okay, so Laetitia, when did you get this light curve? So you mentioned that the science operation started in April. So this is kind of the first observations published so far?
Yeah, I think if I remember well, we obtained this light curve right at the end of the commissioning phase. So, right after the launch, we started 3 months of commissioning just to test all the systems and assess the stability of the instrument and the telescope. And right at the end of this test phase, we observed a few transits of some known exoplanets, and this was the first one. Yeah.
All right. Can you turn off the slide sharing, please?
Yes.
So you get these light curves. Now you get the first feasibility. The first proof of feasibility with this CHEOPS instrument. I read somewhere that people were extremely happy with the quality because it was even better than expected, right? Something like this, like the accuracy of the photometry is like 20% better than expected. Is that correct?
Yeah, for bright stars, we are doing much better than,
that's great.
A bit better than expected.
Is it better because of these stars, or is it because of the instrument itself, or do you not know yet?
Well, I think this is also because of the size of the point spread function. Mm-hmm. So it's a bit larger than what we were expecting based on our ground-based calibrations. And thanks to that, actually, the photometry is even more stable than what we anticipated. So,
so we have 10 more minutes to continue this conversation. And I remind our viewers, some journalists here from Poland, South Africa, Austria, Croatia, Sao Paulo, Greece, India, and Iraq, that they can also ask questions. We will take questions very soon. In fact, we can start pretty soon. Someone mentioned, so I have one question, in fact, here for the science specifically. So these are direct observations of the photometric observation of the star. In which wavelength, and can you do spectroscopy?
No, so we are observing in a broadband filter, so in the visible, in the optical wavelength domain. And CHEOPS is really a photometer, so no, we cannot do any spectroscopy.
So when you say it's a photometer, it means that there is no camera in it, there is only these photometers that react to light intensity?
No, there is a camera, but Kate, maybe you could...
Kate,
yeah, sure. We have Yeah, indeed, we have a single instrument, and we have a CCD, and we take images. So it's a photometer in the sense that we have high precision photometry that we're aiming to get, but we take images which are actually defocus. So you may have seen some of the images which actually show triangularly shaped stars in the field, and this is Laetitia mentioned the point spread function of the telescope. It's defocused and it's triangularly shaped actually because of the way in which our 30 centimeter effective aperture mirror is supported. But this blurring or deliberate de-blurring of the beam means that we're able to get even more precise photometry from CHEOPS, and it's an important feature of the design of the satellite and its payload.
Hi. So I have a question here, another one about the target. What kind of target, what kind of planet are you targeting? Rocky Earth-like exoplanets, and how you do that? Basically, how you define which target you're gonna point to? There is so many stars in the sky that this instrument can observe. So how did you choose those targets?
Yeah. So with CHEOPS, we are targeting stars that we know are already orbited by exoplanets, because these exoplanets have been found by previous missions like CORO, Kepler, TESS, the missions that you mentioned. But CHEOPS is really a follow-up mission. So we know exactly where and when to point to catch a transit, because we already know that there is a transiting exoplanet around the stars we are targeting. Yeah, we are mostly focused on small exoplanets, so planets with size between that of the Earth and Neptune. We know, thanks mostly to the Kepler mission, that this type of exoplanet is very common around Sun-like star. About half of Sun-like stars have a planet like this. So we are now very interested to know more about these planets, and yeah, so so these are the targets we are studying in priority.
So you have enough target right now to keep the mission busy for a while? How many planets do we know in this kind of category?
Hundreds.
Hundreds? Okay.
Yeah.
So that's enough.
We have too many targets.
There is more target than there is time.
Yes.
So how long this... go ahead, sorry, Kate.
I was just going to say, I think a nice feature of CHEOPS is there's also the opportunity for scientists outside the community outside the science team of CHEOPS to use the satellites, so they can propose observations that they would like to make with CHEOPS and can take advantage of the very high photometric precision that we get. So it's a nice opportunity.
Right. So I have some questions coming now. So how many stars can you observe simultaneously?
Only one.
Only one.
Yeah.
That's
this is really this is really the idea of CHEOPS. Like for example, Kepler and TESS, the goal of these missions was to find new exoplanets. So to do this, you need to observe thousands of stars simultaneously to hope catching a transit. With CHEOPS, we are really focusing on observing targets individually to better constrain their transit properties. So we are really focusing on individual targets.
So I have a follow-up question to that. How long does it take to observe it? Are you staring at the same star for 8 hours? Are you moving back and forth? What's the technology? What's kind of observing mode you're using for those observations?
No. So we are staying on the same star continuously for the duration of the transit. Well, usually twice at least the duration of the transit, because we also need some out-of-transit measurements, to calibrate our light curve. Yeah, we are staying on the same target and keeping the star on the same pixels continuously for several hours.
For several hours. Are you expecting to detect some more interesting thing in the transit? Like, I don't know, motion of the transit due to something else? So can you explain maybe this, the famous TTV?
The famous TTV, yeah. Yeah, we could indeed detect TTV. So TTV stands for transit timing variations. So when you have several planets in the same system and these planets are close to each other, they can interact. And because of these gravitational interactions, you can get some time variations in their transit. So sometimes their transit will be a bit early, sometimes a bit late. And by measuring these timing variations very precisely, you can actually detect new unknown planets in the system, or you can also get some information about their mass, actually. So that's also something very interesting to do.
All right. So I noticed that, and one of our viewers mentioned that when you look at the transit, there is this kind of slope of the transit, right? It's not like a sharp drop like you can see when you observe an asteroid, which is something I do a lot. So I recognize that for a transit, you have a different type of profile. So from this profile, first, is it a real profile? And what can you get from this profile? I'm assuming it's related to the atmosphere of the planet, but can you get more about this profile itself?
Right. Actually, this is related to what we call the limb darkening of the star. So the star is not, the stellar disk is not uniform in brightness. It's a bit brighter in the middle of the stellar disk and darker at the edge. And that's why we get this kind of round shape for a transit. So actually, yeah, by observing transits, we can also constrain some useful information about these stellar properties.
So you cannot detect the presence of the atmosphere of the planet?
No, yeah, we could, but to do that, usually you use you're doing a spectroscopy, and so as we said with CHEOPS, we are observing we are doing broadband photometry. So, well, yeah, that's not
okay.
why. Oh yeah, what CHEOPS is.
Something we can do with CHEOPS is to use the more information about the planet's orbit, so measure so-called phase curves as the planet goes around the star, and from that we can infer something about the clouds on the planet. So not necessarily characterizing the atmosphere itself, but saying something about it, the properties, the very global properties of the atmosphere.
So I get a question.
Start to hint.
I got a question related to what you just said. So what will be, and each of you should answer to this question, the most exciting discovery of CHEOPS in the next, 2, 3, 4 years? What will it be? What will, for each of you, of course, it will be a different answer probably, but what do you think will be the most exciting discovery?
That's a tough question.
It's not coming from me, it's coming from a viewer. So
there will be many exciting ones, I'm sure. So it's hard to pick something. Yeah, for example, we are observing a very hot super Earth, which is called 55 Cancri. And we are observing some of these phase curves that Kate mentioned. So we are observing the targets for several full orbits and trying to detect some modulation due to the difference in the light from the planet. Yeah, this planet is really an interesting one. It's so hot that we think it's actually covered with lava. So it could have some kind of big like volcanic plumes or something covering the planet. And by observing this phase curve, we could say more about this exoplanet's atmosphere. So that's a very interesting, yeah, a super IO, exactly.
That's great. Seeing volcanic activity of another planet. That would be a great discovery.
That would be quite an achievement, yeah.
What about you, Kate?
Well, for me, it's also the phase curves. It's observing. I mean, it's trying to study clouds on these distant exoplanets, just to be able to use a simple light curve and the very, very small changes in the light curve as you orbit the planet to say something about the potential composition of the clouds is really exciting. Just to think that we can do that from the ground is yeah, it's quite something. But I mean, there's so much that CHEOPS will do. I mean,
I have one.
As Laetitia said,
something I would like CHEOPS to do, because related slightly to what I do. I would love to find and to have a confirmation of the presence of exomoons.
Yeah.
With CHEOPS, and we should be able to do that, right? With such a good accuracy in photometry. If there is a binary system or a moon around one of the Jupiter, or multiple moon, or even rings, you should be able to see that with CHEOPS.
Yeah, we actually have a program to look for that kind of features in the transit light curves. Yeah.
Excellent.
Fingers crossed.
All right. Well, that's great. So I have one question, like, what is the daily activity for you? What do people often ask? I'm an astronomer. People ask what an astronomer do. So let's not just talk about what you do in general, but what is your daily activity working on the CHEOPS project? What concretely you do? Can you give me an overview of your task, or what is a day of Laetitia working as a postdoc at University of Liege on the CHEOPS project?
Yeah.
And the same for you.
So I'm mostly involved in the exploitation of the scientific data. So we have an online database where we can get data daily. So each morning I just connect to that database, check if there are some new interesting data there. Then I just download them and I play a bit with them, play a bit with the light curve, see if there is something interesting. We also have a lot of meetings between the different working groups working on this project. So this is also part of my daily routine, to exchange with other scientists involved in the project and discuss some interesting findings.
All right, so you look at the data. You may be the first one to see something interesting if you look at the data then.
Yes. Yeah,
like the person who discovered the volcanic activity of Iowa. I don't know if you know the story. She basically was she was an engineer at JPL. I forgot her name, sorry. And when they received the image, when the spacecraft, the Voyager, was leaving, basically the Voyager turned and took an image. And she looked at the data in the morning and she saw the plumes. I said, oh, she was the first person to see volcanic activity on Io by simply looking at the database, which is kind of great. It's a great thing. You can.
It's an exciting feeling to be the first one, spotting something interesting.
What about you, Kate?
Well, I'm looking after this guest observers program on CHEOPS, and at the moment I'm just putting together the details and the tools together with the consortium which will enable people to propose to use CHEOPS. So quite a bit of my time is taken up doing that at the moment. And of course, as Laetitia said, meetings. There are lots of meetings with the beginning of the mission, and there's lots of very interesting things that we're seeing in the data, features that we're trying to understand, data that we're trying to process. There's a lot of discussion on what we're seeing, which is actually very exciting, and I think it's very, very fulfilling because people are coming at it from different directions. Different people are looking for different features in the data, and during these meetings we discuss what different people have found and often come up with some very interesting findings as a result of the different approaches that people are taking. And in doing this, we're improving the output of the mission. I mean, we've only been up and observing for a couple of months now. We've got another almost 3.5 years of the so-called nominal mission lifetime. So we're sort of polishing the mission now and looking to the future.
All right. So the data will be available like we do in the US after a while. Do you publicly release them, or they will stay part of the PI?
Yeah, no, the data will go into the so-called mission archive. There's a proprietary period associated with the data, which is about a year and a half, depending exactly on the way in which the observations are made for an individual target. But yes, eventually the data does become public, and anyone can then access it, of course, for their own science.
Yes, one of our viewers mentioned, do you use complex algorithm like AI to process or analyze the data, for instance? Do you use this kind of techniques at the moment?
No. No.
Yeah, so someone can in the future develop his own algorithm to maybe extract more information on this data, of course. And that's a very positive way to be. If you share the data later on, someone else will make some significant discovery. Like recently, we announced the discovery of an Earth-like exoplanet with the Kepler data by reanalyzing the entire set of data. So this could be done in the future by CHEOPS, for CHEOPS.
Absolutely, the raw data, I mean, all the data products, right from the packets that come down from the spacecraft, all the way through to the processed images, to the light curves, will be available in the archive, and people can take that data and start their own processing and analysis to see what they can dig out of the data beyond what those who propose the observations have found. That'll produce a lot of additional exciting science, I'm sure.
Okay, well, thank you very much. We have done with the 30 minutes discussion. I know we could talk forever about CHEOPS, but maybe one day we'll invite you again to talk about a major discovery with CHEOPS, some kind of exomoons or some kind of volcanic activity detected on another planet, or something even that we don't expect to see. And that's the beauty of science and the beauty of astronomy. We always discover things that we were not expecting to see. So thank you to both of you, Kate and Laetitia, for your time, for participating to our SETI Live. And see you soon, see you again. And thank you to our viewers for following us. Don't forget, you can follow us on Facebook, YouTube, Twitch, on our website. And we will post information about CHEOPS as well on our website, so you can learn about the mission and learn how the progress of the mission. Thanks again, Laetitia. Thanks again, Kate.
Thanks a lot for having us.
Thank you for the invitation and for the chance to chat. Take care. Bye.
Bye-bye.
Bye.